Hey, welcome to the Explainer. Have you ever looked at just a few points on a graph and wondered, how do you draw the one, single, perfect curve that goes through all of them? Well, today, we're diving into an absolutely beautiful mathematical tool designed to do just that, Lagrange's interpolation.
All right, so let's set the scene. Imagine you've got some data, a few scattered points on a graph. You've run some experiments, but you don't have the full picture. So the big question is, how do you find that single, unique, polynomial curve that perfectly nails every single one of your known points? Look, we're not just playing connect the dots with a ruler here. This is about discovering the underlying function that probably describes the relationship between these points. We're trying to make a really smart mathematical guess about what's happening in those gaps. And, as you'll see, Lagrange's method gives us an incredibly elegant way to do it. Okay, so how in the world does this thing work? Well, the genius behind Lagrange's method is actually super intuitive once you see the trick. It doesn't try to build one massive, complicated equation all at once. Nope, it's way cleverer than that. Instead of trying to construct a skyscraper in one piece, think of it more like stacking perfectly designed Lego bricks. Each one of these bricks, or what we'll call a helper function, has a very, very specific job to do. And when you put them all together, they create the final, perfect structure. And the rules for these little Lego bricks are just brilliant in their simplicity. For each and every data point you have, you create one special helper function. You can think of it like a custom-built light switch. This switch is designed to be on, meaning it has a value of exactly 1 at its own home data point, and off, a value of 0 at every single other data point. That's it.
Okay, so these magical helper functions are great in theory, but how do we actually build them so they follow those two simple rules? Well, this is where we have to look under the hood at the math. It's time to check out the formula, but don't panic, we're going to break it down piece by piece.
Whoa, okay, I know that looks like a whole lot of Greek, but seriously stick with me. It's not nearly as scary as it looks. The big sigma just means add everything up. The big pi means multiply everything. The real engine, the real magic is in that fraction. That's what builds our light switches. Let's see how the top and bottom work together. And this is just so clever. Look at the numerator, the top part. It's a bunch of terms multiplied together. If you plug in the x value from any other data point, one of those terms becomes 0. And 0 times anything is, well, 0. That takes care of rule number 2, our switch is off. Then the denominator's job is to make sure that when you're at the function's own home point, the top and bottom become identical, so the fraction equals 1. And there's rule number 1, the switch is on. Perfect.
All right, so now we've got these perfect little switches that are either 1 at their home or 0 everywhere else. The last piece of the puzzle is to give them the right height. So we just multiply each helper function by the actual y value of its home data point. This basically stretches our little Lego brick up or down to the exact height it needs to be.
And now for the grand finale. We just add them all together. Think about it. When you're at one of your original data points, all the other helper functions are 0. They contribute nothing. The only one that's on is the one for that point, and it's been scaled to the perfect height. The result is this beautiful assembly of simple parts that creates one single curve that flows flawlessly through every point.
Okay, theory is one thing, but seeing this incredible machine work with actual numbers, that's where it really clicks. Let's get our hands dirty and put this formula to the test with a real example.
So here's our mission. We've got 4 known data points, and our goal is to use Lagrange's method to figure out the value of our function when x is 10. We're going to find a value right smack in the middle of our data set.
Okay, here are the points we're working with. We've got 5, 12, 6, 13, 9, 14, and 11, 16. So our job is to build a scaled helper function for each of these 4 points, evaluate them at x equals 10, and then just add them all up. All right, first up, let's calculate the piece that comes from our first point, 5, 12. We plug 10 into its special helper function, we scale it by that y value of 12, and boom. The contribution from this first term is 2. Let's keep that number in mind.
Next, we do the exact same thing for our second point, 6, 13. We run the numbers for its helper function at x equals 10, scale it by 13. And this time, we get a contribution of negative 4.33.
Moving on to our third point, 9, 14. We go through the process one more time, and its contribution to our final answer is a positive 11.67. And finally, the term for our last point, 11, 16. When we calculate its value at x equals 10, it adds 5.33 to the mix.
Okay,
We have all our pieces. We've got the contribution from each of our 4 points. All that's left to do now is add them all up and see what we get.
And would you look at that? The total comes out to 1467. That is our prediction for f of 10, a point that sits perfectly on the one and only curve that connects all 4 of our original data points. Pretty cool, right?
So, okay, that's a really neat math trick. But why is this so important? Why is this a fundamental tool in fields like engineering, computer graphics, and data science?
The real superpower here is its flexibility. It doesn't care if you have 3 points or 300. More importantly, it doesn't care if your data points are evenly spaced, which is huge. Real-world data is messy, right? It's never perfect. This method gives you one clean, continuous function, making it an absolute cornerstone of numerical analysis, which is really just the art of finding great approximate answers when exact ones are out of reach.
So, at the end of the day, Lagrange's interpolation isn't just some scary formula. It's a lens. It's a powerful way to find the hidden relationships, the secret stories that live in the spaces between our data. It allows us to model the world and make incredibly educated predictions, so the next time you see a smooth curve drawn from just a few points, you'll know the elegant logic that might just be working behind the scenes. Thanks for tuning in.